Hi all, let me take a look at a couple of problems out of the Achieve 4.3 assignment. The first two here deal with the mean value theorem. So your number 4 in this assignment is going to look something similar to find the value of C. Remember, C is just the x value that is the solution to the mean value theorem. So find the value of x equals C satisfying the mean value theorem for f of x is equal to 7e to the negative 2x plus 7 on the interval of x values from 0 to 2. So the mean value theorem just says that the instantaneous rate of change has to equal the average rate of change. So the first thing I do is I take the average rate of change on this function from 0 to 2, and I can say, well, that's just going to be the function evaluated at 2 minus the function evaluated at 0 over the change in x, 2 minus 0. This goes back to your slope formula, y2 minus y1 over x2 minus x1. So of course our denominator is 2. Our numerator, when I plug a 2 in the function, I'd get 7e to the negative 4 plus 7. When I plug a 0 in the function, I get 7e to the 0 plus 7. Clearly these 7's would cancel, but then e to the 0 is 1, so I have another minus 7 times 1. So I end up with 7e to the negative 4 minus 7. So the 7's that I canceled were these two, but then that gave me another minus 7 in the numerator. Now I have all of that divided by 2. Now keep in mind, what I'm going to do is I'm going to take the derivative and set it equal to this average rate of change, because that's precisely what the mean value theorem tells me. The mean value theorem states that the derivative has to equal this average rate of change for some x value between where this average rate of change began and ended. So I know that f prime of x has to equal this average rate of change for some x between 0 and 2. So I go ahead and I take my derivative. Derivative of any exponential function is that exponential function times the derivative of its exponent. I got negative 14e to the negative 2x. I set it equal to what I had for the average rate of change. First thing I did is I divided by negative 14 on both sides. Gave me a negative 28 in the denominator. Now I saw that I could factor a 7 out of the numerator, and I know that that 7 over 28 will reduce down to 1 over 4. And since I had a negative in the denominator myself, I didn't like that negative, so I went ahead and just said, well, all I have to do is change the order in my numerator to change the signs. E to the negative 4 minus 1 becomes 1 minus e to the negative 4, and I can divide that by positive 4. You didn't have to worry about changing the signs there, but I liked it. I thought it looked better. But now I have e to the negative 2x is equal to this fraction. Then you said, well, how do you solve for x? You've got to get rid of the exponential base e. You do that by taking the natural log of each side. I'll get negative 2x is equal to the natural log of my expression 1 minus e to the negative 4 over 4. Thus, x is equal to that natural log of 1 minus e to the negative 4 over 4 divided by negative 2. Now, I went to my calculator, got the decimal approximation for that, and Achieve asked us to round to 3 significant digits. I got 0.702 in this case. And I know that this is my solution because that value where the derivative is equal to the average rate of change is a value of x equals c. That's between 0 and 2. 0.702 certainly satisfies that criteria. So that would be the answer that they're looking for number 4. Now number 6 is similar, except in number 6 Achieve is going to want an exact answer as opposed to a decimal approximation. So the leading instructions will be find a value of c that satisfies the mean value theorem for a similar function. This time it's a bit easier, 4e to the x on the interval from between 0 and 5. First thing I have to do is find the average rate of change between 0 and 5. F of 5 minus f of 0 over 5 minus 0. F of 5 gave me 4e to the 5th. F of 0, clearly 4e to the 0. We know 4e to the 0 is just 4, so my numerator becomes 4e to the 5th minus 4 over 5. My derivative is the same thing as the original function because the derivative of any exponential function is that exponential function. Technically, it'd say times the derivative of the exponent, but that's just multiplying by 1. So I set the derivative equal to the average rate of change. First thing I did is I divided by 4. That got rid of both of those 4's in the numerator and gave me e to the 5th minus 1 for my numerator. And then you can say, so your answer for x, you'd have to take the natural log of both sides. X is going to equal the natural log of e to the 5th minus 1 over 5. Now, I did go to my calculator just to make sure that this answer was a value of x between 0 and 5. So I got the 3.384 when I evaluated on the calculator. But the answer that achieved once is the exact answer here. So notice the box in the answer is the answer you'll have to input, not the decimal approximation. The only reason I got the decimal is just to convince myself, yes, that answer is between 0 and 5, which it certainly was, but they want the exact notation here. Now, 22 in this section, whew, gorgeous problem, and I do mean gorgeous. So it took me a full page to work it out. We have f of x is equal to the original function x cubed minus 20 over 3x times e to the x plus 7. So we're supposed to find the exact locations of where this function will have any maximum or minimum values, and then state when it increases and decreases. And again, using exact answers. Okay, so I come down here and I take the derivative. You know that this first part of this function, well, second part's easy, derivative in constant 0, but the derivative of this first part, it's a product. So I had to say derivative of the product is the derivative of the first term, which gave me 3x squared minus 20 over 3, times the second, e to the x, plus the first, your group, x cubed minus 20 over 3x, times the derivative of the second, which is still e to the x. At this point, you can see it's easy to go ahead and factor out the e to the x. When you do, you'll be left with x cubed plus 3x squared minus 20 over 3x, and then minus 20 over 3. Now, when I needed to set this equal to 0, guys, what I did for that is I went ahead and went to my calculator, and I typed in the expression you had here, x to the third plus 3x to the second minus 20 over 3x minus 20 over 3. Now, here's the reason I did this, because if I'm supposed to set this function equal to 0 to find the critical points, and I want to find the exact values, I'm hoping there's at least one nice rational answer. This is not factorable through easy means, so the easiest way to do that, other than by hand, is by graphing calculator. So I put my function in y1, a 0 in y2. I'm just going to hit zoom 6. And this is going to show me if there's any roots of this function between negative 10 and 10. Now I can automatically see it looks like it's not crossing at a nice number for this value, that it's not crossing right on. It looks like it's crossing right on here. I'm going to hit second calc 5, and I'll just do enter, enter, enter. And this will show you that, no, that one's not a nice value. That's an irrational number. So that's going to be involving a square root of some non-perfect square value. That's okay. But I'll go over to the right-hand side. Second calc 5, enter, enter. I scroll over here, and I'll find this root. And I can say, okay, x equals 2. Perfect. So automatically, as soon as I found a nice rational 0, I take that 0, the solution, and I use synthetic division to divide it into my other coefficients, the 1, the 3, the negative 20 over 3, and the negative 20 over 3. Please notice when I do synthetic division, you always bring down the first term. 2 times 1 is 2. 3 plus 2 is 5. 2 times 5 is 10. And then I thought of this 10 as 30 over 3. Negative 20 over 3 plus 30 over 3 gave me 10 over 3. 2 times 10 over 3 is 20 over 3. We get a remainder of 0, which guarantees, yes, x minus 2 is a factor, since x plus 2 is a solution. So now when I write f prime of x out in further factored form, I can say, well, I know it had a factor of e to the x. This proves that it has a factor of x minus 2. Please remember, if 2 is a solution, x minus 2 is a factor. So I know that's a factor. Now, My other factor is going to be 1x squared plus 5x plus 10/3. I need to find all of the critical points, so I needed to set this quadratic factor equal to 0. Easiest way to do that is the quadratic formula. Now, I already know the solutions to that quadratic factor. I could find the decimal answers here. I could go second calc 5, enter, I'll guess -7. One of those decimal answers is -4.208. The other one was -0.79 that we already saw. But Achieve is wanting the exact answers. That's why I had to go in and do it out this way. So in here I had 25 minus 40 over 3. That gave me 75 over 3 minus 40 over 3 gave me 35 over 3 inside the root. I wanted to simplify that, but at the same time I didn't want to get a root in the denominator. So in this step I would have thought, well, wouldn't it be best to multiply by the root of 3 over the root of 3 to get rid of that root of 3? But instead of forcing a root of 3 in the denominator, I just multiplied by 3 over 3. Now, the reason that that's simplified is it gave me 2 times 3 is 6 in the denominator. Of course, a -15 for the first term in the numerator. Now, inside of this root, you can think of this 3 as multiplying by the root of 3 twice. One multiplication of the root of 3 cancels the denominator. So then you're left with the root of 35 times the other root of 3 to get you your root of 105. So I can say this is the best exact format of the two critical points. And again, whether you simplify this out on your home screen or else you look at your graphing calculator, these two values are the -15 minus the root of 105 over 6 is the -4.208. The -15 plus the root of 105 over 6 is the -0.792. Now, it's helpful. Even though I don't want those answers, it's helpful to think about where they are in relation to set up your first derivative sign test. So we have 3 critical points. My first region that I'm going to select, the domain of this function is all real numbers from negative to positive infinity. So you break up the domain from negative infinity to the lowest critical point, which is your -15 minus the root of 105 over 6. Then you go from that low critical point to the next critical point, which is -15 plus the root of 105 over 6, the -0.792. Then you go from that critical point to the next critical point at 2, and then you go from the last critical point 2 to infinity. So 3 critical points yield 4 first derivative test intervals. In this first region, again, I'm thinking of this critical point as approximately -4.2. So some number between negative infinity and -4.2, I chose -5. Some number between -4.2 and -0.79, I chose a -2. Some value between -0.79 and 2, I chose a 0. Some number between 2 and infinity, I chose a 5. Now I plug these test points into my fully factored first derivative. So when I did that, I noticed that the first factor, e to the x, no matter what I plug into e to the x, and I always do these by each factor into all of them, I know that no matter what I plug into e to the x is always positive. So I just went ahead and put 4 positives for each of those. Now what about the factor x minus 2? Well, if you plug a -5 into x minus 2, it's negative. Plug a -2 in it, still negative. Plug a 0 into it, still negative. Plug a 5 into it, finally it's positive. What about this quadratic factor? Well, when you plug a -5 into it, you would have 25 minus 25, but then you'd have plus 10/3. The last factor would be positive here. What about when you plug a -2 into it? You would have a positive 4 minus 10. That would give you -6. -6 plus 10/3, still negative. So I can say when I plug a -2 into it, it gives me a negative. When I plug a 0 into it, obviously the x terms cancel. You just have plus 10/3. When I plug a 5 into it, it's definitely positive. You'd have 25 plus 25 plus 10/3. It's going to be over 50. So certainly positive. Now you just look at the product of the signs in your first derivative sign test. Clearly in the first one, 1 negative, 2 positives means our first derivative is going to be negative in that region. The second one, you have two negatives, meaning our first derivative is positive in that region. The third region, one negative, my first derivative is going to be negative in this region. And the last one, they're all positive, so you know your first derivative is positive in that region. Now, please keep in mind that negative derivative means that our function is going to be decreasing from negative infinity to negative 15 minus the root of 105 over 6, and it's decreasing from negative 15 plus the root of 105 over 6 to 2. So you'll see I have that answer right here for my decreasing. Increasing, whenever the first derivative is positive, the function is increasing, so it's going to be increasing from negative 15 minus the root of 105 over 6 up to the negative 15 plus the root of 105 over 6, and it increases again from 2 to infinity. Now, the first question it's going to ask, even before the increasing decreasing though, is when does the function have maximum or minimum values at its critical points? So you go back to its critical points and you say, well, the first critical point is this negative 15 minus the root of 105 over 6. Clearly the function is decreasing before that critical point and it's increasing after it. So anytime you go from decreasing to increasing, that critical point is going to be a minimum. So you'll see I have a minimum at negative 15 minus the root of 105 over 6. But then my function is going to be increasing until I get to the critical point negative 15 plus the root of 105 over 6, decreases after it. So this critical point, negative 15 plus the root of 105 over 6, separates increasing to decreasing. It's a maximum. And then my last one, again, it's going to be decreasing until I get down to 2. It's going to flatten off at 2, and then it's going to increase everywhere after 2. So that means, again, 2 is going to be the location of a minimum. Anytime you go from a negative derivative to a positive derivative, you have a minimum. So notice minimum there. Anytime you go from a positive derivative to a negative derivative, you have a maximum. And so we would have to locate those for our maximum minimums. Hopefully this helps you out with the 4, 6, and 22 in section 4.3. These were some excellent questions. I'll be glad to help you out with any others. Just let me know.